So I have a slide to kind of talk you through each of these ways that the Earth's atmosphere is so important to us. I think all of these are good ways. And as we talk about the Earth's atmosphere, we can actually kind of start to be thinking about the other atmosphere of the other planets. Okay. So the Earth's atmosphere, and this is kind of revisiting the fact that the Earth's atmosphere blocks different types of incoming radiation. So you see X-rays only get so far, ultraviolet rays get a little bit farther within the Earth's atmosphere. Visible light generally just kind of gets through the Earth's atmosphere. Along those lines, we're going to talk about Mars, and Mars basically has no atmosphere now. It used to have an atmosphere, and we're going to kind of talk about how did Mars lose its atmosphere. And Mercury, not massive enough, doesn't have the gravity to hold an atmosphere. And same thing with the moon. So as we talk about, or we think about the Earth's atmosphere, kind of be thinking that Mercury has no atmosphere. Moon, none. Basically what we call an exosphere on the moon. And Mars used to, Venus has a thick atmosphere. So this is what our atmosphere does for us. And so this actually is a similar thing with regard to showing you different forms of electromagnetic radiation. Do they make it through Earth's atmosphere? And this was actually from a previous chapter when we kind of talked about putting, that was just in the same unit. We talked about telescopes. It's very handy to go ahead and have telescopes orbit the Earth. And you see the different types of telescopes looking at the different forms of electromagnetic radiation. So one of the things the Earth's atmosphere does for us is to create what we call a greenhouse effect. And if you're familiar with, and I don't have a green thumb, so I never really have visited many greenhouses, but if you're familiar with a greenhouse, basically it's got a lot of plastic or a lot of glass. And so when the sun is shining, kind of like what this is showing you, when the sun is shining, that would be that yellow bolt kind of coming through the glass and hitting the inside of the greenhouse. Now, among other things, that light actually, as it interacts with matter within the greenhouse, will actually go ahead and heat up that matter. And the thing is that as that matter now is warmer, that is the red particles coming out, and the red particles in a greenhouse are the heat is deflected or trapped, in a sense, by the insulating material, the plastic of the greenhouse or the glass of the greenhouse. So what can come in can't go out, basically, greenhouse effect. And so in the Earth's atmosphere, we have these little particles that actually act as those sort of glass or plastic in a greenhouse. And so here is actually a little video I'm going to show you, or maybe not. Let me go ahead and change my pointer to an arrow and take you out. Now, you're going to see incoming radiation, okay, and that's kind of the stagnant arrows up there. It's much more dynamic than that. You see it interacting with the surface of the planet, and then you see it turning into heat, but you see that heat just oozing off. So actually, this is what happens on planets that don't have an atmosphere or don't have gases within their atmosphere that can act as greenhouse gases. So if I go ahead and add an atmosphere, we can see then, I don't know if that's too much glare for you, but you can see again the incoming energy warming up the planet, and now those little red little blips that actually are thermal energy from the planet that was converted to thermal energy from incoming energy from the star or the sun, now it's all kind of squished around, and we end up with kind of a blanket sort of situation. The planet is warmer, greenhouse effect. So, and greenhouse gases within the Earth's atmosphere that kind of make this happen: water vapor, carbon dioxide. Of course, that's the one that we're all kind of worried about. Carbon dioxide, CO2 is created when we burn fossil fuels. Methane is another type of gas in the Earth's atmosphere that can give this warming effect. So greenhouse gases with regard to the planets, the terrestrial planets, I would say, and you're going to see this with regard to Venus, Venus has its atmosphere is very thick. It's got a lot of gases, and most of its gas actually is carbon dioxide, which is an awesome blanket, an awesome sort of thing that traps outgoing heat. Okay, so greenhouse effect or greenhouse gases are good. Like I said, I think the Earth's atmosphere has done us well with regard to blocking blocking incoming radiation, but also kind of deflecting some of our heat that the Earth would have otherwise given off. We're kind of a little warmer than we would have otherwise been. But I mentioned we're going to have a segment on it. The planet Venus has what we call just a crazy amount of greenhouse gases that essentially keeps it too warm. So the last thing I want to kind of talk you through is the Earth's atmosphere, okay, provides daytime skies are wonderfully blue. Nighttime skies are black, okay? But daytime skies, what happens is that light from the sun actually is scattered, but not all light from the sun. Light from the sun in those shorter wavelengths, okay? So what you see here is actually, let me kind of change my pointer back to so I can draw. Okay, picture the sun up here, okay? And we have Roy G. Biv, all components of visible light coming from the sun. So the Roy G, okay, actually comes straight through. A little bit of the blue, indigo, and violet actually ping-pongs around. Some of it comes through, but some of it kind of ping-pongs around or scatters. We call that Rayleigh scattering, and actually creates blue skies during the daytime. Okay, so that Rayleigh scattering, that scattering of the short wavelengths, the BIV, the blue, indigo, and violet, I've heard like nitrogen and oxygen in the Earth's atmosphere. That scattering, though, also is what gives us our red skies when the sun is low on the horizon. So here we see a person in a different location. The sun is still up here, okay, but, I sneeze. But the sun's light, when it comes through, has more of the Earth's atmosphere to go through. So basically we have the scattering up here, and so by the time the light gets to the person here, this is the sun low on the horizon, it is minus those shorter wavelengths. It's minus the blue, indigo, and violet. And so we have kind of our reds and oranges and yellows coming through. So one of the things I think is neat is when the sun is low on the horizon at sunrise or sunset, if you look at like a speed limit sign, which is kind of white with black markings, you can actually, it looks like somebody is shining a red flashlight on it, okay? Because all of the blue, indigo, and violet has been ping-ponged around or scattered out, okay? And that's all that's reaching you until the sun gets higher and there's less of the Earth's atmosphere it needs to go through. So I just think that is so cool. So one of the things that actually a student recently mentioned to me, she's like, oh, is that why, like the atmospheric effect, pictures on Mars look kind of orangish or reddish? And it's a different type of scattering, a different atmosphere. So yeah. And kind of related to that, if you're on the moon in the daytime, and I might have already mentioned this, but if you're standing on the moon and the sun is overhead, okay, because the moon has no atmosphere, it's going to be like just black around